Dear students, welcome to our YouTube channel Chem Origin. This is Dr. Kumar.
Dear students, in this video module, we discussed about the concept of hydrides in the hydrogen and its compounds lesson. So, in this video module, we detailedly discussed about the hydrides. So, students, these hydrides, generally these hydrides are formed whenever dihydrogen, that is H2 under certain reaction conditions, H2 under certain reaction conditions combining with other elements of periodic table, almost all elements except noble gases, hydrogen is combining with the majority of elements in the periodic table to forms a corresponding hydrides under certain reaction conditions only. So hydrides are formed by the H2 is combining with the other elements in the periodic table except noble gases. So these are called hydrides, and these hydrides are binary compounds. So in detail about these hydrides we can see. The general formula of hydrides is MHN. The general formula of hydrides is MHN or MXHY. MHN or MXHY. Here M represents a symbol of an element. It may be a sodium, this may be a calcium, magnesium. So like that, M represents the element. So the general formula of hydrides is MHN or MXHY. Here M is the symbol of an element. Students, based on the electronegativity difference between the element M and hydrogen, so depends upon the electronegativity of the electronegativity of the atom attached to hydrogen in a binary compounds. So these hydrides are classified into generally three types. So based on the electronegativity of the atom, this electronegativity depends upon the electronegativity of the element attached to hydrogen in a binary compound. These hydrides are classified into three classes. Those are ionic hydrides, second one is covalent hydrides, third one is metallic hydrides. So students, these ionic hydrides, first type of hydrides is ionic hydrides. These ionic hydrides are also called as a salt-like hydrides. These are also known as a saline hydrides. So students, ionic hydrides or salt-like hydrides or saline hydrides are same names. So ionic hydrides are also called as a salt-like hydrides and saline type of hydrides. Second one is covalent hydrides. This covalent hydrides is also called as a molecular hydrides. Covalent hydrides is also known as a molecular hydrides. Third type is metallic hydrides. These metallic hydrides is also known as a non-stoichiometric hydrides. And also these non-stoichiometric hydrides or metallic hydrides is also known as a interstitial hydrides. So these are the different types of hydrides. So in detail about this ionic hydrides and covalent hydrides and metallic hydrides we can see one by one. First type is ionic hydrides. So students, ionic hydrides or salt-like hydrides or saline hydrides. So these are formed by the whenever the hydrogen is combining with the metals of group 1A. So 1A group metals combined with hydrogen, the formed hydrides are called ionic hydrides, and also whenever the hydrogen is combined with the heavier elements of second A group metals like calcium, strontium, barium. So these are the 2A group metals. Whenever the hydrogen combines with the heavier elements of second A group or 1A group metals, it forms a ionic hydrides. Ionic hydrides are formed on heating. Whenever dihydrogen H2 is heated with a 1A group metals or second A group heavier metals, under heating it forms a ionic hydrides. For example, students, whenever H2 dihydrogen is heated with a 1A group metal like sodium, it forms a corresponding hydride, sodium hydride. So this reaction takes place at 300 degrees centigrade. 300 degrees centigrade, dihydrogen is heated with sodium metal, it forms a sodium hydride. So students, these ionic hydrides are non-volatile nature, non-volatile nature. Therefore, under room temperature, these are stable compounds. So these are non-volatile nature, means these are not easily evaporated. Next, these ionic hydrides are non-conducting nature, non-conducting nature. Similarly, these ionic hydrides are crystalline solids, crystalline solids. Ionic hydrides are crystalline solids. So these are the properties of ionic hydrides. Ionic hydrides are non-volatile, non-conducting and crystalline solids. And these are also called as a, ionic hydrides is also called as a salt-like hydrides. Salt-like hydrides. But students, in the second A group metals, the lighter elements like beryllium, magnesium forms the hydrides which are covalent in nature, not like ionic. That's why here clearly we mentioned that heavier elements of second A group. But the beryllium hydride, BeH2, MgH2, magnesium hydride forms a covalent bond, forms a covalent polymeric structures, covalent polymeric structures. Students, the binary hydrides of alkali metals, that is lithium hydride, alkali metals. So students, in 1A group metals we already know the alkali metals. 1A group metals is also called as a alkali metals. So students, these alkali metals hydrides like lithium hydride, sodium hydride, potassium hydride, rubidium hydride, cesium hydride, these are binary hydrides. These binary hydrides have rock salt like structures, rock salt like structures. So the ionic hydrides of 1A group metals forms a rock salt structures, rock salt type of structures. The thermal stability of these alkali metal hydrides are decreases down the group, decreases down the group. From lithium to cesium, the stability of the alkali metal hydrides decreases. Therefore, the thermal stability of alkali metal hydrides decreases from lithium hydride to cesium hydride. Therefore, 1A group alkali metals hydrides are, the thermal stability decreases down the group. So these are the binary hydrides. In case of second heavier elements of second A group metals like calcium, strontium, barium, these hydride stability also decreases in down the group. Therefore, calcium hydride more stable than strontium hydride. Strontium hydride is more stable than the barium hydride. So this is the stability order in case of heavier elements of the second A group. Second A group. Next, electrolysis of solutions of saline hydrides, that is our ionic hydrides. So saline hydrides or ionic hydrides or salt-like hydrides, whenever in electrolysis with molten alkali halides, with molten alkali halides like sodium chloride, potassium chloride, sodium boride, these are produces dihydrogen, these are produces hydrogen at anode. At anode, these electrolysis of saline hydrides or alkali hydrides with molten alkali halides produces hydrogen at anode. So this formation of H2 indicates the existence of H minus. Existence of H minus. Therefore, hydrogen gains an electron and it forms a H minus. This is confirmed by the electrolysis of solution of ionic hydrides with molten alkali halides produces hydrogen at anode. This reaction clearly indicates the existence of H minus ion, existence of hydride ion, existence of hydride ion, that is H minus ion. So during the electrolysis at anode, hydrogen is evolved. The electrolysis of saline hydride solutions. Next, these saline hydrides generally these saline hydrides generally react explosively with water. So students, our ionic hydrides or salt like hydrides or saline hydrides react explosively with water, react explosively with water, because during the reaction of metal hydrides, during the reaction of ionic hydrides with water, H minus is released. This H minus ion is highly unstable, so it is immediately, very rapidly, very speedily reacts with the water and release, convert and forms hydrogen and forms H2 dihydrogen. So students, whenever ionic hydrides treated with water, if you add a water with ionic hydrides or salt like hydrides or saline hydrides, these are reacts violently or explosively, because during the reaction between ionic hydride and water, the released unstable H minus ion reacts immediately, rapidly with water, releases a dihydrogen gas. And suppose for example, if you see sodium hydride is added to water, it releases H2 gas with the formation of sodium hydroxide. Sodium hydroxide. And this lithium hydride is unreactive. Lithium hydride is unreactive at moderate temperature, means at room temperature or close to room temperature. Lithium hydride is not that much reactive like other alkali metal hydrides with oxygen, with dioxygen O2 or with Cl2 gas. So students, lithium hydride is not that much react with oxygen and chlorine at moderate temperatures. Therefore, that's why in order to prepare other hydride compounds, generally we prefer lithium hydride. For example, if you want to prepare other hydride compounds like lithium aluminium hydride or lithium borohydride, we can prepare under open temperature, under open atmosphere, in even though, because at moderate temperature lithium hydride is not that much reactive with oxygen and chlorine. Therefore, generally lithium hydride is used to prepare other hydride compounds like lithium aluminium hydride or lithium borohydride. So students, whenever lithium aluminium hydride is treated with AlCl3. AlCl3, students, we know it is a electron deficient compound. It acts as a Lewis acid. So whenever lithium aluminium hydride is treated with AlCl3, it forms lithium aluminium hydride. Lithium aluminium hydride, and along with it releases HCl. HCl. Similarly, students, when you treated lithium hydride with diborane, its formula is B2H6. So whenever diborane is treated with lithium hydride, it forms lithium borohydride. Lithium borohydride. So students, lithium hydride is useful to prepare other hydride compounds like lithium aluminium hydride or lithium borohydride. See students, boron is a third A group element. Aluminium is also a third A group element. So lithium aluminium hydride, lithium borohydride, we can prepare with the help of lithium hydride. So students, these are the about these are the details about the ionic hydrides or salt like hydrides or saline hydrides. So next hydrides is covalent hydrides. Covalent hydrides. Students, just now we discussed about the ionic hydrides. Ionic hydrides is formed by the dihydrogen is combined with the 1A group metals or heavier elements of the second A group elements forms ionic hydrides. Here the covalent hydrides. The covalent hydrides is formed by the covalent hydrides. Covalent hydrides is formed by the dihydrogen is combined with a p block elements. P block elements. For example, carbon, nitrogen, oxygen, fluorine. So these covalent hydrides are formed by the dihydrogen is combined with a p block elements. If dihydrogen is combined with a 1A group metals or heavier elements of second A group metals forms ionic hydrides. But covalent hydrides is formed by the dihydrogen is combined with the p block elements. P block elements. So students, in these covalent hydrides, the popular examples are methane, CH4, ammonia, NH3, H2O, water molecule, HF, hydrogen fluoride. So students, in the CH4, hydrocarbons. Hydrocarbons are the examples of covalent hydrides. These hydrocarbons are classified as a alkanes, alkenes, alkynes and aromatic hydrocarbons based on the this general formula. If the hydrocarbon is having the formula CnH2n plus 2, these are called alkanes. If the hydrocarbon is having general formula CnH2n, these are called alkenes. Alkenes. And if the general formula is like this CnH2n minus 2, these are called alkynes. Alkynes. Or if for example for aromatic hydrocarbons, the popular example is benzene. Benzene. Its molecular formula is C6H6. So students, detailing about alkenes, alkanes and alkynes, aromatic hydrocarbons we can see in the next lesson, organic chemistry. Organic chemistry lesson we can detailing discuss about the alkanes, alkenes, alkynes and aromatic hydrocarbons. So just now you can remember here these alkanes, alkenes, alkynes and aromatic hydrocarbons are the examples of covalent hydrides. Covalent hydrides. So students, these covalent hydrides, the name itself denotes there is a covalent bond between the atom and hydrogen. Atom and the hydrogen. So generally these covalent hydrides are further classified into three types based on their number of electrons and bonds in their Lewis structure. So number of electrons and bonds in their Lewis structure, covalent hydrides. Covalent hydrides are further classified into three types. Those are electron deficient molecular hydrides, electron precise molecular hydrides, electron rich molecular hydrides. So electron deficient molecular hydrides, electron precise molecular hydrides and electron rich molecular hydrides. So detailing about this electron deficient, electron precise, electron rich molecular hydrides we can see detailing one by one. First type is electron deficient molecular hydrides. So students, these electron deficient molecular hydrides, the best example for this is diborane. Diborane. The molecular formula of diborane is B2H6. B2H6 diborane. Students, this is a electron deficient compound. About this diborane and this diborane structure we detailedly discussed in the third A group elements lesson. So students, I hope you are all very familiar with the structure of the diborane. So students, if you see diborane, in case of diborane, the ground state electronic configuration of boron is 1s2, 2s2, 2px1, 1s2, 2s2 and 2px1, the 2py0 and 2pz0 in case of ground state configuration of boron atom. In the first excited state, one electron from 2s orbital is jumped to the 2py orbital. As a result, in first excited state, the electronic configuration of boron is 1s2, 2s1, 2px1, 2py1 and this pz orbital, 2pz orbital is 0, vacant. Therefore, in the diborane molecule, due to availability of vacant 2pz orbital, boron can accommodate a pair of electrons. That's why this diborane is a electron deficient compounds. So students, if you see the structure of diborane, there are four terminal hydrogens and two bridged hydrogens is present in the diborane molecule structure. So these are the bridged hydrogens. These bridged bonds, these are called bridged bonds, or these are looks like a banana. That's why these bonds are also called as a banana bond, because this bridged bond between boron, hydrogen and boron, these are also called as a 2 electron 3 centered bond. So these type of two bridged bonds are present in diborane and 4 terminal boron hydrogen bonds are present in diborane. So in this diborane, the bond between boron and hydrogen is a covalent. So this is the example for electron deficient molecular hydride. Next type covalent hydride is electron precise molecular hydride. So students, this electron precise molecular hydride, the best example is hydrocarbons, that is methane or ethane. These are the very good examples for electron precise molecular hydrides. Students, you know the structure of methane and hybridization of carbon in methane already we learned in the chemical bonding lesson. So in methane, the hybridization of carbon is sp3 hybridization, and the geometry of the methane molecule is tetrahedral geometry. So students, we know carbon's atomic number is 6 and its ground state electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz0. This is the ground state electronic configuration of carbon. In the first excited state, one electron from 2s orbital is jumped into the 2pz orbital. Therefore, in first excited state, the electronic configuration of carbon is 1s2, 2s2, sorry, this is a mistake one here students, 1s2, 2s1, 1s2, 2s1, 2px1, 2py1, 2pz1. So in the first excited state, there are 4 unpaired electrons present in the carbon. These 4 unpaired electrons formed a four covalent bonds by overlapping with the unpaired electrons of 4 hydrogen atoms. As a result, we are getting a stable methane molecule. In methane molecule, carbon is having octet configuration in its valency shell. So for electron precise molecular hydride, the best example is methane. So students, in methane, the hybridization 1 s orbital and 3 p orbitals are involved in the hybridization. As a result, the hybridization of carbon is sp3. These 4 sp3 hybrid orbitals overlapped with the or form a covalent bond with 4 unpaired electrons of 4 hydrogen molecules, and 4 hydrogen atoms forms a corresponding methane molecule. The hybridization of carbon in methane is sp3 and geometry is tetrahedral. Next, Next, electron rich molecular hydrides. Electron rich molecular hydrides. So the good examples for these electron rich molecular hydrides are ammonia, water, HF. Students, we know the structure of ammonia and also we know the structure of water. So about the structure of ammonia, hybridization and geometry, and the structure of water, hybridization and geometry of water molecule, we already very clearly learned in the chemical bonding lesson. Chemical bonding lesson. So students, we know ammonia. In ammonia, nitrogen is having a one lone pair on nitrogen. In ammonia molecule, one lone pair is present on nitrogen atom. In case of water molecule, there are two lone pair of electrons. There are two lone pair of electrons present on the oxygen atom. Whereas in case of hydrogen fluoride, fluorine has three lone pair of electrons. Three lone pair of electrons. So that's why these are the examples of electron rich, electron rich, electron rich molecular hydrides. Ammonia, water, HF are the examples of electron rich molecular hydrides. For example, if you see students, ammonia, the in ammonia nitrogen's atomic number is 7, we know very well. So the ground state electronic configuration of nitrogen is 1s2, 2s2, 2px1, 2py1, 2pz1. So these three unpaired electrons overlapped with the three unpaired electrons of three hydrogen atoms and forms a corresponding ammonia molecule, the 2s2. So these are the lone pair of electrons. We are denoted with the Lewis symbols, ammonia. Similarly students, if you see water molecule, in water molecule, oxygen atomic number is, we know very well, 8. Oxygen atomic number is 8. Its ground state electronic configuration is 1s2, 2s2, 2px2, 2py1, 2pz1. So it has two unpaired electrons. These two unpaired electrons overlapped with the unpaired electrons of two hydrogen atoms and forms a H2O molecule. These two lone pairs are, one lone pair represents the 2s2 and the other lone pair represents the 2px2. So this is about water molecule. If you see hydrogen fluoride, so students, fluorine's atomic number we know very well. Its atomic number is 9 and electronic configuration is 1s2, 2s2, 2p5. So it has only one unpaired electron. This one paired electron combinedly sharing with the unpaired electron of hydrogen and forms a HF molecule. Therefore in HF molecule there are three lone pair of electrons on fluorine atom. So this one lone pair represents 2s2 and the second lone pair is from 2px2 and the third lone pair is from 2py2. So these are the examples of covalent hydrides: electron deficient molecular hydrides, electron precise molecular hydrides, and electron rich molecular hydrides. So students, this is about the covalent hydrides. Next type of hydrides is, students, metallic hydrides. Metallic hydrides. Metallic hydrides. So students, we discussed about the ionic hydrides and covalent hydrides. Ionic hydrides are formed by the dihydrogen is combined with the S block metals, that is 1A group metals, and heavier elements of the second A group metals forms ionic hydrides. If the dihydrogen is combined with the P block elements, it forms a covalent hydrides. If the dihydrogen is combined with a D block elements or F block elements, D block elements or F block elements, if the dihydrogen is combined, the formed hydrides are called metallic hydrides. If dihydrogen combined with D block elements or F block elements, the formed hydrides are called metallic hydrides. Metallic hydrides. Students, in the D block elements, particularly dihydrogen combined with elements of group 3 group 4 and group 5 only. Selectively in the D block, group 3, group 4 and group 5 elements generally hydrogen combined to form a hydrides, and also hydrogen dihydrogen combined with F block elements to form a corresponding metallic hydrides. Corresponding metallic hydrides. Students, in the D block, we know at the middle of the D block there are group 7, group 8 and group 9. So these group 7 and group 8, group 9 elements dihydrogen do not combine to form a hydrides. So this is called as a hydride gap. Hydride gap. Hydride gap. In the D block elements, group 7, group 8, group 9 elements, this dihydrogen does not combine to form the corresponding hydrides. So this is called as a hydride gap. Hydride gap. So this is very important note, students. What is hydride gap? Next, these hydrides conduct heat and electricity. These hydrides, these metallic hydrides conduct electricity and heat. Heat and electricity conducted through these metallic hydrides, passed through these metallic hydrides, but not that much efficient their parent metal. Not that much efficient like their parent metal. The parent metal means the whichever the element of the D block the hydrogen is combined is called the parent metal. But anyhow, these metallic hydrides are conduct electricity and heat. But students, just now we discussed ionic hydrides or saline hydrides or salt-like hydrides or non-conductor of electricity and heat. But these metallic hydrides are non-stoichiometric hydrides. That's why metallic hydrides is also called as a non-stoichiometric, because for example, students, if you see LaH2 2.87, see the stoichiometry, it is not follow strictly stoichiometry. It may be H2 or H3, but it is LaH2 2.87, ytterbium H 2.55, titanium H 1.5 to 1.8. So these metallic hydrides are non-stoichiometric. That's why these metallic hydrides is also called as a non-stoichiometric hydrides. But students, we saw the ionic hydrides or saline hydrides, or similarly we can saw the covalent hydrides. There is a stoichiometry is maintained, but in case of metallic hydrides it does not follow stoichiometry. Non-stoichiometric hydrides are existed. Therefore these metallic hydrides is also known as a non-stoichiometric hydrides. Next, students, these metallic hydrides are generally similar to the properties of their parent metals. Their parent metals properties shows. So just now we saw the examples. LaH2. If you see LaH2, it exhibits the properties similar to the lanthanum. Or it exhibits, if you take ytterbium H2, it exhibits the properties similar to the its parent metal ytterbium. Or if you take ZrH, zirconium, so this metallic hydride shows the properties similar to the zirconium metal, similar to the its parent metal. So the properties are similar to the parent metals in case of metallic hydrides. So students, these metallic hydrides are very hard, and it is also having metallic luster. Metallic hydrides are very hard and also having that metallic luster, and are also, we saw just now, these are good conductors of heat and electricity. And also these metallic hydrides exhibits magnetic properties. But students, the density, these are less dense than the parent metal, but the density of metallic hydrides are less than the parent metal of the metallic hydride. Similarly, these are generally used as a catalyst in hydrogenation reactions. Students, metallic hydrides are used as a catalyst in hydrogenation reactions. So this is the important note, students. In your higher studies, we can see the examples of hydrogenation reactions. Hydrogenation reactions. There we can see the examples for hydrogenation reactions. So just now you can remember metallic hydrides are used as a catalyst for hydrogenation reactions. Hydrogenation reactions. Next, metals like, suppose metals like palladium or platinum can accommodate a large volume of H2 gas, can accommodate a large volume of H2 gas and used as a hydrogen storage, used as a hydrogen storage. So students, generally the metals like palladium or platinum can accommodate a large amount of hydrogen gas on the surface of the metal like palladium and platinum. Therefore, these are used as a hydrogen storage media. Hydrogen storage. So in order to store the hydrogen gas, these palladium or platinum metals are used. So, and is used as a source of energy. Source of energy. So about this hydrogen storage and about the hydrogenation reactions, you can clearly learn it in your higher classes. Okay students, I hope you enjoyed this session. So students, in this video module we learned the hydrides concept of hydrogen and its compounds lesson. So in this video module we clearly discussed about the hydrides and types of hydrides, that is ionic hydrides, covalent hydrides and metallic hydrides. So I hope you enjoyed this session. Thank you very much.